lecture number 5, if you recall, we learned about propagation delay. So whenever there's a change in the input, before the output changes, there's a small amount of delay, and we refer that delay to as a propagation delay, which is in the order of few nanoseconds, which is a very tiny delay, but sometimes it rarely happens, but that delay can cause a glitch. So today's lecture is we are going to find out whether our digital system has a glitch or not, and if there's a glitch, how we can avoid that. Okay. All right. So just a quick review on. So we also learned in that lecture that different families of CMOS and TTLs, they have different propagation delays, and you can see things have got a little better. It's now down to like 5 nanoseconds. These are the timing waveform for different gates that we are going to do today. A few terms that you need to know. So if you look at it over here, TR, that's known as the rising time. What rising time is actually the amount of time it takes for the logic to go from 0 to 1. Okay, that is the rising time. The TF that you see here is a falling time. When there's a change in the input goes from 1 to 0. The amount of time it takes to go from logic 1 to 0 is referred to as a falling time. If you look at the output, this is actually an inverter. So 0 here, 1 would be here, 0 here, 1 here, 0 would be here. Two things here that you need to learn, which is TPHL, the time delay for the logic going from high to low. So notice it's going from high to low. So this time period is known as TPHL. Okay. And similarly, this one, when logic goes from 0 to 1, you see it takes a pattern. It doesn't go straight up. It takes some kind of progression and goes to the high level logic. And that time is referred to as TPLH, going from low to high. And the average propagation delay that they use, the industry, the manufacturer they use, they actually take a mean of these two values and come up with average propagation delay for different kind of chips. So I pulled these numbers from data sheets for different gates that we actually used in lab number 1 when we were doing simulation. For inverter, TPHL is 15 nanoseconds and TPLH is 22 nanoseconds. So the average propagation delay will be a mean of these two numbers. So 27, that would be 13.5 nanoseconds. 7408 AND gate is 18 nanoseconds. NOR gate is 15 nanoseconds. And an OR gate is also 15 nanoseconds each. Okay, so let's move on to the first example that we are going to do today. Okay, so I have this this circuit. This is I just randomly come up with this circuit. Initially, the values are such that A is set to 1, B is set to 0, C is 0, and D is 0. Okay. B here goes from 0 to 1, so meaning that B goes from 0 to 1. So it's maybe the F would change, how long it would take. That is what we are going to find out in this example. So how much delay to see the new value of F? So at the back of your supporting material, you see a graph paper. We're going to use that, but we're going to quickly come up with an expression for this circuit. We know this is the AND gate, so this is going to be A dot B bar. This is again AND gate, so this is going to be CD. This is a NOR gate, so A dot B bar plus CD, and then we have bar on the whole thing because it's an opposite of OR, right? I'll just go ahead and write my expression for F over here also. Okay. Initially, we had A equals to 1, B equals to 0, C and D both equals to 0. And then B goes from 0 to 1. Okay. All right, so we will actually going to create a timing waveform looking at this expression right here. So we'll try to come up with the timing waveform for the initial values first. So we know A is initially set to 1, so it's actually 1. On the x-axis you have time, okay, in nanoseconds. Remember, you have 0 logic here and then you have 1 here, correct? C is also, C and D both are 0. So this is 0 here, and D is also 0. Okay. Now B was initially 0, but then it goes to 1. So initially it was 0. Here's a transition, it goes to 1. Okay. Okay. I'm going to work through this expression right here on top right, and I'm going to start off B bar, which is the inverter. So B bar, what would be B bar here at this point right here? It's going to be 1, right? Because B is 0, so it's going to be 1. And it's going to be 1 all the way till this time period right here. Now notice here, logic goes from 0 to 1. What would happen here? Will this immediately go to 0, or there's going to be a delay before it gets to 0? Yes, David? There's going to be a slight delay, okay? There's going to be a slight delay, and then it goes to 0, okay? We will refer this delay as a propagation delay. In if you look at the, how much was for the inverter? Inverter, it was, okay, all right. Is this a TPHL or a TPLH? TPHL, right? Because it's going from high to low. So TPHL. And how much it is for 7404 inverter? It's 15 nanoseconds, right? So we will just write down here 15 nanoseconds, and this is for the inverter, okay? I'm now going to work on A dot B bar. So A dot B bar, we know it makes an AND gate. A is 1 all the way, right? And B bar, okay, so here both inputs are high. The output is actually going to be high until it gets to here. Now here, B goes from 1 to 0, okay? Any of the input going into an AND gate, output is going to be 0. So will that go to 0 immediately, or there's going to be a delay here? There's going to be some delay here, correct? Okay, so it's going to stay 1 for a little more amount of time, and then it goes to 0. Okay, so we will refer, this would be a delay here. Is this the TPHL delay again, right? Because you're going from high to low. So TPHL, and this is for the AND gate. How much is the delay for the AND gate? It's 18 nanoseconds. Okay, now I'm going to move to this part of the expression CD. Notice C and D both are 0, so C ending with D will be just a straight line on 0, correct? Okay, and now I'm actually going to move on to the last part, which is the F. Okay, and it's making a NOR gate. So basically it's between these two, and it's making a NOR gate. Okay, what's the property of a NOR gate, folks? If any of the input is high, the output is going to be 0, correct? Okay, because input is high here, so remember this is 0, okay? This is 0, this is 1, okay? Any of the input high, output is going to be 0. Now here the output goes from 1 to 0. So is it going to go up right away, or there's going to be some delay here? There's going to be some delay here, right? So there's going to be some delay, and then it goes up. Okay, and again this would be is this TPLH right here, because we are going from low to high, and this is for the NOR gate, and the delay was how much? 15 nanoseconds. So the total propagation delay here is going to be the sum of the delay for at the end of each individual gate. Okay, so if you add those numbers, 15 nanoseconds plus 18 nanoseconds plus 15 nanoseconds, how much is the total here, guys? 48 nanoseconds. Okay, so what does this mean, this 48 nanoseconds? This means initially when A was 1, B equals to 0, B, C, D were equals to 0, but when B changes from 0 to 1, the change in the F is actually going to take 48 nanoseconds before you will see a change. Okay, make sense? Right? Shall we move on to the next example? Is everybody following me? Okay, all right. So here's one example. We have a truth table. Okay, we are going to come up with an expression first. So let's fill the table. So we got 2, 3, 4 minterms here. 3, 7, 6, and then 4 right here. I'm pretty sure everybody would agree that 2, so 3 would be here, right? 3 is here, 4 is here, 6 is here, and 7 is here. 0, 1, 2. Okay. All right. So how would you make a pair here? I think everybody would agree we can make 3 and 7 and 4 and 6. Is that okay? Okay. What would be the expression for this? So here, this will be, so we got X here, and then we got Y and Z here. So what would be the expression here? Y, Z, correct? And for this rectangle, that would be what? X. All right. So it would be Z bar, correct? X, Z bar. Y, Z plus X, Z bar. Okay. I went ahead and made the combination logic diagram for this example. And here we have a scenario where X, Y, and Z, X, Y, Z, X, Y, and Z all are set to 111, meaning right here, both X, all 3 variables X, Y, Z set to 1, and our output is 1, correct? Now, what's going to happen? X and Y stay 1, and let Z transition to 0. So they're referring to this one. X and Y remain same. Z changes from 1 to 0, right? And you would think F will still remain 1, right? Because the output for that is also 1 in the truth table. Let's see. Let's go to that graph paper. Okay, I'm just going to write the expression that I got from the K-map over here. YZ plus x z bar. Okay, initially the conditions are, so we have x, y, and z. They are all 1. Okay. However, z goes from 1 to 0. Okay. We'll do exactly the same way we did in the previous example. So I'm going to start up with my initial values. So x is 1. Y is also 1. Z is initially 1, but then it goes to 0. Let's work through the expression. Let's get z bar first. So z bar, we will have up, it's because it's an inverter, so this will invert of 1 would be 0, so it will be 0 here. Now here the logic goes from 1 to 0, right? So obviously there's going to be a small delay here. It doesn't it doesn't go up right away. It takes the small amount of time, okay, and then it goes up. Okay, all right, so there's a small delay here. We're not going to worry about like how much is the delay at this point. Okay, I'm now going to work on this expression x z bar. Okay, x is 1. We know this is making an AND gate. X is 1 all the way. Okay, so what would be the output here, folks? 0 till here. Now the logic goes from 0 to 1 at this point, which would mean our output will also go 1, but it's going to be a small delay before it goes to 1. Okay. Now let's work on YZ. Okay, Y is 1 all the way, as you can see, and Z is also 1, so the output here will be 1 for first 2 cycles. What happens here? This goes from 1 to 0. So what would be what would happen to the output here, guys? It'll go to a 0, but there's going to be a small delay, correct? Sorry, this is the only and the last boring lecture. After this, it will be very exciting. Okay. Okay, all right. So we got everything. Now we're going to work on that F thing. F, which is basically OR gate, correct? All right. Any of the input is high, output is going to be high. This is high, so it's going to be high all the way. Okay. Now, what's going to happen here? You see, it's going to be high, but here logic goes from 1 to 0. It stays high for a very small amount of time, and then it goes to 0, right? Here, the logic goes up again. So after a small amount of time, it goes up 1 again, and then it stays 1 because this is high, right? So what's happening here, when my F was supposed to be 1 for a very small of time, it went to 0 and came back to 1. This is what we know as a glitch in our system. This is also referred to as a static 1 hazard. And static hazard basically refers to the risk of the output going to 0 when it was supposed to be 1 all the way. Okay, does everybody following me here? How did we get this glitch here, right? Okay, all right. Now, the next part is how we can avoid this glitch. Well, the easiest way to avoid this glitch is through the use of the K-map. Now remember, whenever you have two adjacent rectangles and they are disjointed, there's going to be a glitch. Okay, now do we have two adjacent rectangles in this K-map? Notice this rectangle right here is adjacent to this rectangle, correct? There's no connection between these two rectangles, so that means there's going to be a glitch. Okay, so remember that. If there is a disjoint between adjacent rectangles, there is a glitch. Okay, and because we are taking the min terms here, so this is SOP, so static 1 hazards only happens in SOPs. Okay, all right, so remember that. So what are we going to do here? Whenever we have this kind of situation, we actually connect the two rectangles. And how can I connect these two rectangles? Yes. 6 and 7, so I can actually add another rectangle here, 6 and 7. Unfortunately, one of the advantages of that, you're going to have one extra term in your expression, but this way we would be able to avoid the glitch. Okay, so this would mean you're going to have extra term here, and what would that be extra term? What is the expression for that? X, Y, correct? Right? We would call this term consensus term. Okay. All right. We'll go back to our grid sheet right here. So now my expression changes to yz plus xz bar plus xy. Okay. I'm actually going to move this f right here to over here. So it was for the first 2.5 cycle, it was high, and then it went 0 for a very small time, and then it came back to 1. Okay, so let's do xy now. Xy. X and y both are set to high, and x and y makes an AND gate, so they're going to be high all the way, correct? And notice this consensus term is actually also independent of the z, which is actually changing from 1 to 0. Okay, now the new f with the consensus term is going to give you an output which is going to be what? It's going to be high all the way, right? Right. Even to the glitch, because this is high, the output is going to go high. So this is with the consensus term right here. And this way we can actually avoid a glitch in our digital system. Okay, we're going to stop here.